Yeah, thank you. Let me put the title first. Okay, so this is a joint work with ongoing joint work with Petr Somberg. So let's start with the classical situation. Classical case. So we have a G, our semi-simple, semi-simple the algebra complex over C. So now we have the root space decomposition like n minus by Exum, Levy, n plus, where n minus and n plus are the positive and negative new radicals, and L is the Levy subalgebra, and n plus is the positive new radical, n minus negative radical. And now we, so P is parabolic subalgebra given by Levy. Here I'm taking the n plus in my notation. So for the parabolic case, before the when my G is SL, and we have this thinking diagram like this. Now I'm trying to define the Kostant differential step by step. So let's consider X from the parabolic P and alpha from the graded algebra of n plus. So the action alpha is given by, also I should also mention n plus is spanned by theta i's onto n. Bigger. Okay. Oh, sure. Is it okay? Okay. Alpha. This is the contraction map. Sorry. Theta I with alpha. Also n minus is spanned by the dual elements, which I call by theta lower n. This is theta upper I and theta lower I. Okay. So now the action of P on radical 4 times V, where V is any UG module given by X acting on alpha 4 times smaller V X acting on alpha 4 times V alpha action of X on V, or we can take the representation pi of UG, and then we can use the action of UG on V like this. So the differential map is given by K n plus V smaller V the is acting on V. So this can be again rewritten as this I chain theta chain theta I is one, and the rest is the same. Since for the one graded case, this will commute, so the whole term, this first term will vanish for the one graded case. One graded case. This will goes away. So the only contribution will come from the second part. And it can be shown that this gives to 0. Number 1. Number 2 is partial is UP equivariant. Meaning is X from P action of X with this on this partial Q minus partial Q with action of X. This goes to 0, or their Lie bracket, if we write in terms of the Lie bracket, this gives 0. So this is in short, this is the short description of this Kostant differential in the classical case. Now what we want is to define address the same problem for the Q version, quantum case. So what we have to do, we have to have this analogous version of this wedge product in terms of Q. So we need Q here, we need Q here. So as in last talks, we have seen that this Q wedge power of V is given by the Wallenstein-Spinagle, and this is defined by the braiding operator. So I should write in a proper way. So let's consider the wave with a full subcategory of UQG, and the braiding and U and V full subcategory. UV are the objects in OF. So the braiding UV is given by the flip and the R matrix, universal R matrix. And we can have also the normalization of this, normalization of VUB, which is denoted by sigma of VUB. And I mean, if we if we try to define this guy, so this guy will defined as the kernel of sigma I comma I plus the identity. And so this object is nothing but so we are defining it on the nth tensor power, where the change is happening on the ith. So sigma I comma I is given as the identity tensor dot 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 sigma. So it is appearing in the ith and I plus 1th place, and rest is the identity. So in this way, we can define this guy. So here we notice one thing that the only the part the giving this contribution, it's we have this contraction map here. So we need contraction map for the quantum settings. So maybe I could. Do I have enough time, or I'm running out of time? Am I running out of time? Or? Okay, sure. Yeah. So this is given by summation AJQ Bhattacharjee. So alpha has the expression theta1 qs theta2, which is actually coming from the idea of this thing. And okay, so theta. So this is the dual pairing between n plus and n minus in the quantum case. And it shows that so there is an equivalent statement following are equivalent. Number one is AJQ is minus Q to the power inverse AJ minus 1Q, or AJQ is minus Q to the power minus of J minus 1. Number two is Q version of contraction map is UQL invariant. So UQL is, in this case, UQL, I mean, if my G is, UQG is, for example, let's say UQ SL3, in this case, it will be given by UQ SL2 4 times the central element. Or classically, if we have this guy, so according to our Dinkin diagram notation, so this 2 by 2 block and this 1 by 1 block. So in the Q version, we take all the generators from the E1 and F1, and we generate this UQL from that. So this coefficient is unique up to this UQL equivariance condition. So this is so if we have this contraction map here, so we can easily go to the Kostant differential map, and we can build up the Kostant differential for the at least for the parabolic case. But I don't have enough time. But I have also for the general Grassmannians, we can also do that. So yeah. Thanks. I mean, I tried, but it shows that the classically what we have is the same goes for the Q version, exactly the same, exactly the same.
Okay, let's have a speak again.